Assalamu alaikum. I welcome you all to a fresh series on power electronics. We will try to cover all the topics that we missed to record during the last recording session. So in the today's class, we will discuss about the Chuck converter, which is a very famous converter made after the name of a famous scientist, Solomon Chuck, who invented this converter in 1970s, and it became so famous that it is included in most of the textbooks for the power electronic system. So let us start with the basic philosophy of the Chuck converter, and then we will move into the same procedure that we adopted for the derivation of the inductance, capacitance, and the switch realization processes that we have seen for the buck converter, the boost converter, and the buck boost converter. So let us start with the with this particular topic on the Chuck converter. Before we move into the Chuck converter, the philosophy behind the Chuck converter is very simple. So let me first of all draw all the three converters, and we will see what is the requirement or what is the need of designing a Chuck converter. This is a conventional buck converter. Right here we have the boost converter. I am drawing it with this BJT, although it can be realized by using any other switch. And here we have the buck boost converter. Now let us assume that all of these three converters are operating in a continuous connection mode, and therefore we have this kind of inductor current for all of these three basic converters. Now if you notice here that this input current, this is Is, it only flows when we have this switch in the connection mode. That is, when we apply the gate pulse or the control signal to this particular switch Q, only then we have the input current flowing. That means that for a buck converter, in a CCM mode and in a steady state condition mode, we have this type of a shape of the input current Is. For the boost converter, we have the inductor connected on the input side, and therefore the input current is continuous. However, on the output side, we have this type of discontinuous output current. And surprisingly, for this buck boost converter, we have input current, this is I in, and we have this type of output current, which is the I naught. Notice here, all of these three basic isolated converters have one inherent problem in it. For a buck converter, we have a discontinuous input current. For a boost converter, we have a discontinuous output current, and for the buck boost converter, we have discontinuous current on both the input as well as on the output side. Now this means that we require to have some filters to be part of these converters in order to smooth out the current ripple component at the switching frequency, which is drawn by the line supply in case of a buck converter and by the load in case of a boost converter. So this discontinuity in the input current or the output currents actually create problems for which are known as the EMI problems. And you should notice that the EMI problems are generated if we have an abrupt variation in energy flow. So you can see here that we have this input current which is discontinuous, and therefore this abrupt variation in the input current cause severe EMI problems in a buck converter. So this EMI problem become even more horrible when the converter operates in a discontinuous conduction mode. Now in here, if you see, despite the fact that all of these three currents, this current, this current and this current, which represents the current of the inductive element present in these converters, the inductor current is continuous, which means that we are operating in continuous conduction mode, but yet we are having a discontinuous input current for a buck converter, a discontinuous output current for a boost converter, and a discontinuous input as well as the output current for a buck boost converter. This problem was solved by the renowned scientist Lobert and Chuck. So he came up with an idea that instead of having a discontinuous input current and a discontinuous output current, we can achieve the same result of the voltage transfer ratio for a buck boost converter by having a two inductor topology, which will have a continuous input current as well as a continuous output current. So let us move on to the topology which is proposed by this Lobert and Chuck and understand and derive the transfer function of that particular topology. So the topology for the Chuck converter is very simple. Let us say we have here, this is Vg. Here we have the inductor. We have a series capacitor instead of having a capacitor in shunt. This is L1, this is L2, and we have an output which is very much similar to that of a buck converter. So this is C2, this is R, this is C1. In here we have actually a switch that can toggle between this position number 1 and this position number 2. So first of all, let us define the polarities here. This is plus, this is minus, VL1. So we have the current flowing here is this IL1. Then we have plus, minus, this is VC1. We have plus, minus here, this is VL2, and here we have the IL2. This is C2. Here we have the IC2. This is the I0 or the load current. This is V0. So the procedure is exactly the same, that we will draw the equivalent circuit based on the switch position. So at position number 1, the equivalent circuit is something like this one, that we have so this is VL1, this is IL1. Here we have this is plus, this is minus, this is VC1, plus minus, this is VL1, this is L2, C1, C2, plus minus, this is R. Similarly, for switch position number 2, we have this is Vg, and then we have the capacitor C1, this is C1, VL1, IL1. Here we have the IL2, this is VL2, this is the V0, this is I0, R, C2. So that's it. Now further to this thing, we will now write down the appropriate equations based on the Kirchhoff's voltage law and the Kirchhoff's current law, and we will apply basic principles of the energy storage element like we did for the buck converter and the boost converter. We will apply those laws to identify some of the key equations that are necessary to find out the voltage gain or the transfer function of this given converter. So for this position number 1, the key equations are, that is VL1 is equal to this Vg, and that is equal to L di over dt. Also we have VL2 that is equal to minus Vc1 minus Vc2, and to further simplify, we can say that this Vc1 is equal to V1 and this Vc2 is equal to V2. So that becomes equal to minus V1 minus V2, and that is equal to L2 di by dt. This is L1 di over dt, and we can say this is L2 di over dt. Okay, let us we can also write it as di2 over dt, but nevertheless it is giving us the concepts here. The other thing is the IC1. So the current through these capacitors C1 is equal to IL2, and that is equal to I2. Let us say that the current here, which was flowing here, this is IL2, this is equal to I2, and here we have the current that is equal to I1. So that is equal to I1, and here we have the current equals to I2. So, and also we have this is equal to C, this is equal to C1 dV over dt, dV1 over dt, and here we have the IC2 that is equal to I2 minus I0, and that is equal to I2 minus V2 over R. So if we apply the small triple approximation, so we can actually replace these small letters by a capital letter. So this is equal to V2 over R. So these are the equations for the switch position number 1. Similarly, we will write down the equations for the switch number 2 here. So we have VL1 that is equal to Vg minus V1, and that is equal to L1 di over dt, di1 over dt. Similarly, we have this VL2 that is equal to minus V2 that is equal to L2 di2 over dt. Also, if we apply the expression for the current IC1, then IC1 is equal to I1, that is equal to C dV1 by dt, and also we have the IC2 that is equal to I2 minus V2 over R, and that is equal to C dV2 by dt. Now these equations provide us the foundation for analysis of this Chuck converter. Next, we will apply the volt second balance on these equations to find out what is the transfer function of this given circuit. For this switch position number 1, this is Vg, and during the time the switch is at position number 1, VL1 becomes equal to Vg minus V1 during the time we turn the switch to position number 2. So here we have, this is DTS, this is D dash TS, and this is VL1. Similarly, based on this thing, I can write that this VL1, the average value VL1 should be equal to 0. It is equal to D times Vg plus D dash into Vg minus V1. Similarly, for this switch, for the position number 2, for the inductor VL2 is equal to minus V1 minus V2, and on the above side this VL2 is equal to minus V2. Let us take onto this side and write it as this minus V2, and this is D dash TS, and this is DTS. Also, we should notice that for a steady state condition, the inductor volt second balance should be fully accomplished, and therefore the average voltage across this inductor VL2 should be equal to 0. So that is equal to D times minus V1 minus V2 plus D dash into this minus V2, and that is equal to 0. So now we have two equations. So let us first of all expand this equation for VL1 and see what we get. So here we have D times Vg plus D dash Vg minus D dash V1, that is equal to 0. Vg into D plus D dash and that is equal to d dash V1. So V1 is equal to Vg over d dash. This is my equation number A. On this particular side we have minus V1d minus V2d minus V2d dash, that is equal to 0. So if I expand this particular equation, then I get V2 becomes equal to minus V1d, and that is my equation number B. Now if you plug in the value of this A into this equation number B, then we have this V2 becomes equal to d over d dash minus with this Vg. So here we obtain the value of V2 as a function of the input voltage, which is Vg. To find the transfer function ratio, we will use equation number C, which gives us a very straight value that V2 over Vg is equal to minus d over d dash, that is equal to minus d over 1 minus d, and this is exactly the same as that of a buck boost converter. So we have no change in the transfer characteristics when we compare it with the buck boost converter. However, the additive advantage here is that we have two inductors in place which ensure that we have a continuous input current. This ensures continuous input current, and the inductor L2 ensures the continuous output current under the CCM mode. Therefore, we have obtained a transfer function which is exactly the same as that of a buck boost converter. In the cost of having one additional capacitor and an inductor, we have solved the problem of the discontinuous input and the output current for a traditional buck boost converter. So in the next step, we have to find out the values for the components that are used in this particular converter. So for that, let us first of all find out the capacitor value for C1. So for the C1, we do know that the rate of change in the voltage dV1 over dt is equal to I2 over C1, and for the switch position number 2, it is equal to I1 over C. So we will use these equations, these four equations. We will use these two equations for finding out the value of the capacitor, input capacitor and the output capacitor. Now notice here one thing, that this output stage of this chuck converter during the time when the switch is connected with position number 1 and the switch and the position when it is connected to position number 2, it is exactly the same as that of a buck converter, and therefore whatever expression we have derived for a buck converter is equally implementable for finding out the value of the output capacitor for this particular converter. So what we are left with is only the input capacitor, which is C1, and for that we will use equation these two equations. So we draw the characteristic, we draw the waveform for the capacitor voltage. So this is the sort of a capacitor voltage here. We have this is V1, and this is the delta V1. The slope here is equal to I2 over C1, and the slope here is I1 over C1, and this is for the time dts, and this side is for d dash ts, and this whole is actually the switching time or the ts of the switch. Now if we know what is this delta V1, then this is the starting point, this is the ending point. So delta V1 is equal to slope times the duration during which the slope continues to drop from this initial point to this final point, and that is equal to d time ts. So we have C1 is equal to I2 over delta V1 into d into Fs. Now here we have this I2, which is not a function of either the input current or the output current, but we do know that the average of this I2 has to flow through the load, and that is equal to V naught over R, and therefore this C1 can be expressed as V naught D into R delta V1 into this Fs, right. So this is the expression for the capacitor C1. As I have mentioned that since the output stage of this Chuck converter is same as a buck converter, so C2 is equal to C naught of a buck converter. So the C2 which is C naught here is equal to delta IL2 divided by 8 delta V2 into this Fs, which is the switching frequency of this particular converter. Similarly, we can find out the value for the inductance in this particular circuit. In order to find out the switch that can be realized for this Chuck converter, we will use the same terminology as we have used for the previous non-isolated converters. Let us copy this one for the switch realization. Here we have this is the Chuck converter. So here we have two switches. So when it is, let us say that we have, this is switch number 1 and this is switch number 2, and both of them work in complement with each other, such that we have switch number 1 operating, then this switch number 2 is off, and when this switch number 2 is on, then switch number 1 is off. So I can say that this S1 is equal to this S1. So I can say that this S1 is equal to S2 complement. Now in here, the inductor current will define the polarity of the current flowing through a given switch, and therefore for this switch S1, the polarity of the current is that we have the current flowing through in this particular direction. So this is plus, this is minus, and for this switch S2, this inductor current shall have a path in this fashion. So this side is positive and this is negative. So again we have the for both the switch S1 and S2, we have a positive flow of current. As far as the voltage is concerned, when this switch S2 it is closed and this is open, then this particular point and this particular point shall have a voltage difference which is equal to, let us say this is A, this is B, then VAB is equal to VA minus VB, and VB is grounded, so VAB is always greater than 0, and therefore this device, whatever device we want to have on the switch number 1, it should have a capability of blocking the positive voltage, and therefore this S1 can only be a BJT, it can be a MOSFET, it can be an IGBT. As far as the switch number 2 is concerned, if we have, for example, this switch is now off and we have turned on this switch, then we have this positive side is connected with ground. Let us say this is point C and this is point D, then VCD is equal to VC minus VD. Now this VC is negative, it is 0. However, we have, with the negative sign, we have a terminal voltage here, and there we have a positive voltage, so it always have to block the net negative voltage across itself, and therefore this is somewhere we have this switch S2, and S2 should be a diode here. It should be a diode. So if I redraw this particular circuit, then this circuit is, we have a switch here, we have a series capacitor, Here we have the here we have the diode here, and this is C2, this is C1, this is L1, this is L2, this is R, this is V0, and that's how we realize this particular converter. As far as the this converter is concerned, this converter has an inverse polarity at the output, so it can only be used in those applications where the reversal of the polarity is not a big issue. So that's all for today. I hope that you have understood this converter very well. So till the next lecture, take care and Allah Hafiz.